Are you having a good first day? This beat is going kinda hard. I feel the same way. I've waited my whole summer to watch this man's lectures. Music's too loud? You can't hear me? Let me turn up the mic a little. Test, 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 test. The hat, I'm just feeling it today. I'm just feeling the hat. You'll see too, the pink goes well with the color scheme that I'm trying to use in my notes. It's just the whole ensemble. It brings it all together. Estes lecture number 2. Oh, hey! You were in road vehicle? Zeron says, what's this? No Twitch advertisements? Yeah, hopefully not. I'm a CSE student, but I'm here to give the stream love. Hey, thanks for coming. You are very welcome. Talking about F1 cars all day. I think by the end of today, I'm going to watch an episode of that F1 show on Netflix. I'm getting into it a little bit. What's it called again? Like Race to Survive or something? I just started, so I'm on season 1. Like maybe 2 or 3 episodes in. Drive to Survive. It's worth checking out. It's worth checking out. It's fun. The best show if you watch the races too. Yeah, I need to watch just more F1 in general. Some of the stuff is over dramatized or not entirely correct, but the behind the scenes stuff is juicy as hell. Yeah, it's cool to see the inner workings of the teams. How it's just so high pressure. I think in the first episode there's what was the team? Anyways, they were in like 5th place at a race, and they'd never been in that nice of a position before. And the car pulls into the pit, and you know, whenever you come into the pit stop, they take off the wheels, put them back on. Somebody on the team didn't put one of the wheels all the way back on. And I mean, this happens in like, 3 seconds? It's like, bzz, bzz, wheels on and off. Yeah, and then, yeah, and it wasn't just one car, because every Formula team I learned, they put 2 cars in every race. The same guy didn't get the wheel back on for both of the cars. Oh, that's a bad day for the pit crew. Yeah, it was Team Haas. Same thing in 2019. Oh no. I guarantee that person probably isn't on their team anymore. Haas is such a bad team. Hey, they're trying. Dr. S is glad to see you're doing well. If you remember, it's Ryder. Hey, Ryder. Yeah, I remember you. I remember you. You had this hot sauce that you were having people try, and it was like something Scoville, like 50 billion, and it was. That's dangerous hot sauce. Dangerous. Red Bull. Alright, people. It's 3:02. I think I'm gonna back off the music a little bit here. And we're gonna get this flight dynamics class started. Man, I'm excited. I'm excited to do flight dynamics with you. It's definitely a weird semester. Everything being remote. Holy cow, right? But I think we're gonna have a good time. I think we're gonna have fun. So I'm really looking forward to this. Car dynamics and flight dynamics in the same day. That's right, we're taking the world by the ground and the air. Yeah, what are we? We're missing the sea is what we're missing. All right, listen up, guys. What I'm thinking for today, we're gonna try to quickly blast through the syllabus. Let me. Aha. We're changing the Twitch scene here. I'm gonna turn off night mode so the screen doesn't look orange. Yeah, I have this new Twitch set up. It's pretty fun. How about feet dynamics? Hey, that's next level. That's next level. So first we're gonna blast through the syllabus, and then we're going to go into our first set of lecture notes. Now, if you go to UB Learns, let me pull this up. If you go to course documents, if you go to notes, it almost didn't show up for a second. I was like, where is it? If you go to class handouts, there's a PDF, and this is what I'm going to go through today. And you're going to see there's a lot of blanks. So we're going to fill this in together. So I'm going to try to get these out a little bit earlier in advance if I can, so that you can print this out and follow along, or you can just download the PDF and annotate this on a tablet, because that's what I'm doing. And so while we're going through the syllabus, you can get this ready to go. All right, let's go back here. Everybody doing all right today? If you want to join in the chat, wait, down there, you got to make a Twitch account. It's free. And that's how you interact. I'll try to keep up with questions and stuff. But that's what we're doing. All right, let's get started. Okay. So you can see I was updating this late last night. Okay. So I won't go too much into the course description as we look at the syllabus, because part of the lecture content is talking about the course. So I'll just skip this for now. But we're talking about flight dynamics. And this is me, your instructor, Dr. Aaron Estes. And I just blanked this out here on Twitch. But you can see this if you get the PDF on UB Learns. And so I got my email. For office hours, I'm going to try Discord. I haven't tried it for office hours yet, but I think it has some interesting features. So I'm kind of interested. Now, Mondays and Thursdays, a pro gamer move, yeah, using Discord. I know. So Mondays and Thursdays, I'm going to be there from 4:30 to 5:30. And then our TA, Saeed, he's going to be there Wednesdays and Fridays. So every day except Tuesday, you're going to be able to go to this Discord link, and it's the same link for the TA and me. So every day except Tuesday, you can go there from 4:30 to 5:30, and you can chat video like you can on Zoom using Discord. You can also, I put a little math bot in there so you can type like LaTeX formulas if you're into that. But yeah, we'll see how that goes. Course meetings. Can you post a PDF of the handout annotated for today only? Next class, I can be set up for it. Can you post a PDF annotated? Oh, yeah. My plan is to, I'm going to write on these handouts myself, and I will post the copy that's filled in by me as well. That's my plan. So like if you miss one of these, You can always go back to the video and fill in the handout yourself, but I do plan on also posting my completed notes for reference. That's my plan. Will that be posted every class? There might be a little bit of a delay, like a couple days delay after the class, but they'll be up quick. I'm going to try my very, very best. Are the printers in Capen available? Not totally sure. That's an excellent question. I would think so. Like, they can't turn off the printers. Does anybody know that? Okay, you heard they're printing, but it's a new system. Okay, Dr. Darrell does the same. Kiosks are up and running. Self-serve printing, that's nice. Right, that does bring in some money, the printing. Okay, course meetings. We go from 3 to 4:20 on Monday, Wednesdays. Fridays, we're going a little shorter, 3 to 3:50. So it says recitation. On Fridays, it'll kind of depend what we do. Like Fridays, I want to do more examples, but if I get a little behind on lecture Monday and Wednesday, then I'll use Friday as like a catch-up day. So plan on being here Monday, Wednesday, Friday. Just think of Friday we'll run a little bit shorter. And we meet here every time. So we'll keep it on Twitch. Just a quick description. If you're new to Twitch, you'll figure it out pretty quick. Let's see. Yeah, come to every lecture. That's my advice, because that's going to help you keep up with the content. Flight Dynamics is really fast-paced. It's a very fast-paced course. So I'm coordinating with Dr. Lagore's section, and we're trying to keep exactly the same pace, and it's a very fast pace. So I want you to come to every lecture so that you won't fall behind. Because once you fall behind, it'll be a little bit hard to catch up. The easiest way to stay up to date, just come to every lecture. Okay. Textbook. Yeah, we'll get to that next page. Twitch chat, just be kind and courteous, common sense. Treat others the way you want to be treated. And other than that, have fun. I mean, Twitch is a fun platform. I don't know, I kind of enjoy this. This is a more stressful time, COVID, but this is kind of just like a fun platform. We can get together, relax a little bit, learn. So we're all, yeah, and a lot of us are gamers here. So, I mean, a lot of us are on Twitch anyways. Yeah, I enjoy Twitch. I just discovered chess on Twitch. Like, I'm no good at chess, but there's this guy, Hikaru. Do you guys know Hikaru? He's this grandmaster chess guy, and he streams chess. Anyways, super entertaining. I'm into that recently. Okay, let's see. Oh, textbooks. Perfect. So the primary text we're using, Flight Dynamics Chess Tourney, I would come in last place. We could though, isn't it free, like chess.com? Oh, that's such a good idea, Flight Dynamics Chess Tourney. So this number one, this is the book that we're primarily going to use. It's by Nelson, Flight Stability and Automatic Control. Now the nice thing is, if you go to UB Learns, let's do that. We have the first 6 chapters of that book here in PDF format. Or wait, the first 5 and then chapter 9. So we got the book right here. Beautiful. Beautiful. Okay. Yeah, like it says here, the Nelson textbook, that's the primary source, and the excerpts are available online. I am not a student. Can I watch? No, you may not. No, of course you can watch. And I remember you, COD gaming lover. You took digital controls with me. Happy to see you here. Okay, let's talk about the course requirements. You've already probably seen assignment number 1 is posted on UB Learns. And we're gonna try to have like a weekly rhythm of homework. So my homework is posted at 2 p.m. on Mondays, and then it's due 2 p.m. the next Monday. And I'm just gonna try to keep that going. So just get in the rhythm of being used to that. So if you add it up, it's going to be somewhere between 10 and 12. Like we probably won't have a homework like every single week, but expect that number of assignments. And then for this class, we are doing 2 exams. And so there's a midterm and a final. And these are the dates that we're planning for. And we'll give you more details about that. But what I think is some of it is going to be like a conceptual test, and I think that'll be online. So expect an online conceptual portion, and then expect a take-home portion that you'll probably have like 24 hours to work on. So more details to come, but that is my understanding of the tests right now. Now, in terms of the weighting of the assignments, it's most of the weight falls on the homework assignments. Okay, so if you have like 10 to 12 homework assignments, that's 60% of your grade. So make sure to do every homework and keep up with that. Come to office hours and work through it. And then that midterm and final I mentioned, each of those is 20%. Let's see, what else do I want to mention here? Here's our tentative grade breakdown, but you know, we might change these a little bit just depending on how the class is doing. Okay. And then, like, this is posted on UB Learn, so you can go through this in more detail. Okay. And then we have, like, a tentative schedule week by week. So go through this at your leisure. Let me know what questions you have. And that's what we're doing. The main takeaway, I think, is stay engaged, keep up, be proactive about, asking questions. If you're confused, don't feel like you're the only one. That is a myth, my friends. I went to college, obviously, at one point, and I would be in like a math class, and the person next to me, it seems like they know everything, and I was like, gosh, I must be the only one here who doesn't know what's going on. I find more often than not, if you have a question, the majority of the class also has a question. So, so just ease up on yourself a little bit. Be free to ask questions. Don't worry, guys. This class will be fun. Yeah, I think so. Okay. With that, I'm going to switch modes to our notes for the day. Oh, good. Okay. Will the Twitch lectures be recorded and posted to be viewed at later dates? Okay. The nice thing about Twitch, as soon as this lecture is done, the video gets saved to my Twitch page. On top of that, I take the video and I export it to my YouTube channel. So to find my YouTube, there's some information on the syllabus, but just search Dr. Estes in YouTube and you can find the videos there as well. To reiterate though, come live, stay engaged. But if you ever miss a lecture, don't worry. You can catch up on it later in the day. All right, guys. Let's get into it. I'm really excited to hang out with you guys this semester. I think it is a privilege. It really is a privilege to be a professor and to get to interact with you guys. You're very talented, and so yeah, I just wanted to say that. I feel like it's a privilege. All right. What is this course about? Okay. So it's flight dynamics, but let's break that down a little bit. We will study the kinematics. So that's like position, velocity, acceleration, angular acceleration. The kinematics and dynamics. So that's how like the forces and moments affect the kinematics. You guys know this. Of aircraft. Okay, why are we doing it? For the purpose of analysis, simulation, control, and design. So we're going to learn the theory so that we can make some high-level decisions about aircraft control and design. So next I want to talk about what types of problems we're going to solve, because that'll unpack this a little bit, make it a little more clear, I think. Okay, so what types of problems are we going to solve? So the first problem, we'll have like homework on this kind of stuff later. How do you set control surface and thrust conditions on an aircraft to achieve certain steady state flight conditions? Let me give you an example. So like an example of that. Let's say I want to achieve level non-accelerating flight. So at some like constant velocity with a certain rate of descension. Like we're preparing to land a plane or something. So if you give me some flight condition like this, how are you going to set the control surfaces? Like the elevator angle, the thrust condition, that sweet cruise altitude pointing down. If you guys have seen Dr. Disrespect doing a flight simulator, have you seen that? He just drives it right into the ground. Flight simulator games are not easy. Okay, let's look at another type of problem. So, how do you process sensor measurements from an aircraft to determine its position, velocity, acceleration, and altitude? So, for example, how to process sensor readings. Got banned. Yeah, that's right. How to process sensor readings from, let's say, an IMU, an inertial measurement unit. So this is pretty cool. I think it's, I forget which homework number it's going to be, but we have data from a quadrotor, and so this has an IMU on it. So we have angular rate readings from the gyroscope, we have readings from the accelerometer, and we're going to give you that data from a real quadrotor flight. And using those sensor measurements, we're going to teach you how to reconstruct the flight path. And there's different ways to do it, like using Euler angles, quaternions. Where I know in intermediate dynamics you learned a bit about quaternions, so we'll use that formulation. So this is like a nice practical skill you're going to get out of this class. If you have sensor readings from an aircraft, are you able to reconstruct what the aircraft was doing, what kind of forces it was experiencing? I like that one because it's a nice like practical skill. And then so I'll leave you with this one. This is the type of problems we're going to like finish the course with. How do you design a control system for an aircraft to handle a certain way? Now, I know many of you, actually, are any of you taking continuous control systems right now with Dr. Singh? He's a control systems guru, by the way, at the University of Buffalo. I bet probably a couple of you are taking that. I know aerospace engineers have a really packed schedule, though. It's hard to squeeze in those other ones. Nobody? So we will design basic stability and control augmentation systems to meet given handling quality metrics. So we'll talk about like the flight envelope and certain quality measures that are standard for flight. And then, so if you want an aircraft to handle a certain way, have like, you might have certain overshoot settling time conditions, like we learned in dynamic systems. We're going to learn about basic controllers to make the aircraft behave that way. So it's cool, that connection between some dynamic systems theory and now we're applying it in flight systems. Dr. Estes is the OG. Hey, thank you. Okay. All right, we're going to get into an example here. So we're going to look at a 1 degree of freedom pinned airfoil. Why are we doing this example? So a lot of the analysis we're going to do in this class, it's going to involve nonlinear differential equations. And you'll see that we're going to develop this, but the equation of motion for this pinned airfoil is nonlinear. So just telling you right out of the gate, aircraft equations are nonlinear differential equations. However, it's very popular to linearize these equations around some equilibrium point and then use those linear differential equations to do analysis. Dakota says rip. But linearization is our savior. Okay? So this example kind of encapsulates the type of analysis we'll have to do with linearization, and so that's why we're doing it. So let's say this is a pinned airfoil. So P here is the pin, and let's say it's like a frictionless pin joint. So this airfoil can rotate about that, and we are providing this relative wind that's parallel to this like gray line here, and U infinity, that's our relative wind velocity. All right. This line on the airfoil is the chord line. So it's connecting like the leading edge, the trailing edge. The angle between the chord line and this relative velocity, we call it alpha, the angle of attack. And these variable definitions, I'm kind of, if you have the handout, you can scroll ahead a little bit. So that angle of attack is the second point here, the angle between the chord line and the relative wind. All right, so this represents the CG right here. And that's where weight is going to be. Oh, I'm going to keep using pink. That's where weight is acting, assuming that gravity is acting just straight down. And that's going to create a moment about this frictionless pin joint. Yeah, there we go. W is the weight vector. Let's put a little arrow on top of it. For vectors, I'm used to using a line underneath the variable. Do any of you guys do vectors that way? I'm retraining myself to do the arrow on top for this course. Nobody does that? Yeah, I think the arrow on top is more popular. But it takes a little more effort to draw. Come on. Only Ringgit did that? Did Ringgit do the arrow underneath for aerodynamics? Arrow on the bottom seems crazy to me, says Opie. Well, I don't do an arrow on the bottom. I just do like an underline. Okay. Anyways, I digress. I'm going to use arrow on top for vector. Okay. So the COP, that is the center of pressure. So that's where we can resolve the pressure distributions into just a lift and drag force, and we'll resolve it along the chord line here. So I'm going to put a lift vector generated by the pressure differential here, and I'm also going to put a drag vector. And just as a refresher, the lift and drag, well, the lift acts perpendicular to the relative wind. So you can see, like, if the relative wind's coming in this way, I got a 90 degree there. And the drag acts parallel. And I think I mentioned that a little bit. Fake news? Arrow on the bottom. Vector notation, man. It's a very polarizing topic. Fake news, man. Okay, so we got the center of pressure, we got the lift, we got the drag vector. Okay, last thing here. We are going to be dealing with some actuated control surfaces in flight dynamics. And so the tail of an aircraft, that's where we see the elevator. So that's the little control surface at the, trailing edge of the tail that we can actuate, and it makes an angle here, delta E. So that's the elevator angle. Yeah, let's limit the political discussion in the chat. Okay. Now what we're going to do next is we're going to make some assumptions. Because we're going to work towards getting an equation of motion from this. So we're going to have to sum the moments about that pin joint, but we're going to make a couple assumptions first. Number one, we're going to assume that the angle of attack is small. And the reason we're doing this is I want to assume that the angle of attack is small enough that the moment about the pin created by drag is negligible. So angle of attack is small. Well, how small? I'm employing this assumption so that it's small enough so that the moment about the pin created by drag is negligible, so I can ignore it. Let me scroll back up to the picture a little bit here. Let's just zoom in. I mean, you can see that we got the pin here, and the drag vector has that little moment arm about the pin. So that's the so we're saying the angle of attack is small enough that we assume that this lever arm is going to be so small that, okay, the drag just creates a negligible moment. So once we start summing moments, we'll just forget about it. Okay, that's assumption 1. Assumption 2, and I think I already mentioned this, but we're going to assume pin joint is frictionless for now. So that means if there is an angle of attack rate, it's because usually friction is creating a force proportional to velocity. So we're going to neglect moment created by friction. So we're going to assume that that pin joint, it doesn't create a dissipative torque or anything as this guy rotates. Okay. Assumptions 1 and 2. Okay, so now we're going to get to the equation of motion. So we're going to sum the moments about the pin joint P, and we're going to use this sign convention, which is kind of opposite what you might usually see by the right-hand rule. So we'll consider moments that go this way to be positive. So we're going to have the moment of inertia about that pin joint times the angular acceleration is going to be the sum of moments. So that's just Newton's second law. How about I bring this picture down here so we can have it as, or wait. I could write the sum of moments up here with the picture, and then I can copy and paste it down lower. So that's what we're going to do. Okay. That's what we're going to do. So we're going to sum the moments about P. And just, we're going to assume this direction is positive. Ooh, I forgot something important here. We got to define some distances in this picture. So the distance from the pin joint to the CG, let's call that L1. So we need that moment arm. We need that moment arm. The other one, we need the distance from the pin joint to this center of pressure where the lift and drag is applied, and let's call that L2. Okay, so the first moment, was P chosen for any reason, or is the position arbitrary? A little arbitrary in this case, along with the center of pressure in CG as well. Okay, so the moment about P caused by the weight, that's going to be a positive moment, and it's going to be L1 times the force, and then we're going to need cosine of the angle of attack, because that's going to be this perpendicular distance. Is the pin not at the trailing edge of the wing? No, in this case, this pin joint is close to the leading edge. So we're summing about P at the leading edge. Okay. Now, from one of our assumptions, we said that the moment caused by the drag is negligible. So, we'll ignore that moment. But the moment caused by lift, so it's going to have this lever arm. So that's going to be minus L2 times the lift force, which I'm going to put it here as a function of alpha. We'll get to that in a second. Cosine alpha. And finally, so we considered the weight, we considered the lift. From our assumption, we're ignoring the drag. But the final piece is the moment on the wing is also affected by this elevator angle, okay? So we're going to add an additional term. This is going to be a moment coefficient for the elevator times the deflection of the elevator. Shrek says that is an elevator at the trailing edge, which can rotate, but is not the pin. I thought the same thing at first. Okay, thank you for clarifying that. So there is a pin joint here that the elevator rotates about. Thank you guys in the chat for clearing that up. I really appreciate it. Feel free to always type that stuff in and help out, because I might not say something the most clearly all the time. Okay, so the pin that we're summing about is like up here. So this whole airfoil, I mean, I don't want to make this too messy, but it could like rotate, say like here. So it's rotating about that pin joint. That's what we're summing the moments about. And then additionally, the elevator rotates about that pin at the end, and that also affects the moment. Okay, so that concludes our sum of moments for this example. And I'm just going to rewrite this equation down below. Okay. So this results in the nonlinear equation of motion, L1 times the weight, cosine of the angle of attack, minus L2 times the lift force, also times the cosine angle of attack. Wait, I won't put parentheses because I didn't put it for the other one. And then minus this moment coefficient for the elevator times the elevator angle. And I'm going to take all this stuff on the right-hand side. And for some of the analysis later on, we're just going to call this a function of the angle of attack and the elevator angle. Okay? So the moment of inertia about the pin times the angular acceleration is equal to a nonlinear function of the angle of attack and the elevator angle. So we've just figured that out by using Newton's laws. So why is it that the angle of the elevator times the moment? Well, this is not a moment itself. We call it a moment coefficient, which is kind of a little bit like a hand wavy thing, saying that if you deflect the elevator a certain amount, that's going to create a moment that's proportional to this coefficient. So it's kind of like a spring constant creates a force. You have like K times X equals a force, right? So in a similar way, I'm saying like this moment coefficient times delta is creating a moment. Okay? So that coefficient is not a moment itself. What is the significance of that blue arrow distance? I don't know what you're talking about, my friend. Oh, this one. That's just a moment arm. So like a moment is a force times the perpendicular distance about a joint. So about this pin joint over here, kaboom, I have this lift force L, which is acting at this point down here. Or wait, I was talking about, that was for the drag force. So I was talking about the drag. So I got this force, and then the perpendicular distance is right here. Yep, for the first assumption. We didn't label it, so I wasn't sure if it came into play. Yeah, thank you for asking. But yeah, that was for the moment created by this drag. We're ignoring it. We made a simplifying assumption. Okay, yeah, right. I didn't put it in the table. Okay. So, equilibrium solutions. So this is the first question I want to ask. Let's say we fix the elevator angle to a specific angle. Whew. Wondering if there are additional considerations that matter if you fully resolve the airflow with fluids calculations to find... Yes. Short answer to your question, this is just a simplification. We're resolving that relative airflow into, if you integrate over the surface, you can have these simplified point loads. M or mu in the moment formula? Pretty sure mu. Oh, this is a capital M. I'm just using like a capital M. In another setting, would that matter? Sure it would. We're just starting. Think of this. This is a simplified example that we're starting with to illustrate how, even for a simple case, you get a nonlinear equation of motion. But in most applications, even like serious commercial flight, you're going to convert these to linear equations. And that'll be suitable most of the time. Okay. So if we have a given fixed Q's gangster's parrot, good grief. Learning about flight dynamics when flight simulators at an all-time peak. Also makes sense. This also models structural response suitably already. Yeah. Okay, so we're going to say, what if I fix this elevator angle to like 5 degrees? Let's assume that it's not moving around. Is there an equilibrium angle of attack where the airfoil remains fixed? So imagine this. You have this pinned airfoil in a tunnel. You have some incoming wind with some velocity, and I fix the elevator angle. Is this, if I configure the airfoil at a certain angle, can I find one so that it'll just stay there, fixed in the wind? So at equilibrium, this is what equilibrium means. The angular acceleration will be 0. And the angular velocity will be 0. That's just a mathematical way of saying this airfoil is fixed. It ain't going anywhere. If the angular acceleration is 0, that means that the right-hand side of our equation of motion, which, remember, the right-hand side was the sum of moments, that's going to add up to 0. So I have this function f on the right-hand side, which is the sum of moments. If the angular acceleration is 0, then this right-hand side must be 0. So all this is saying is the right-hand side, if you plug in this equilibrium angle of attack, if it exists, that right-hand side should be 0. Okay, so the first thing we're going to do, we're going to solve for that angle of attack. It does indeed exist. So we're going to use this condition here to solve for it. So let's take the right-hand side of that equation and set it equal to 0. Okay, so I'm just going to grab it. I'm going to grab it from up here. Copy. Paste. And what we're going to do, we're going to substitute in that this is at the equilibrium. So we have to add these little subscripts that indicate, oh, and I got to even put one in here, that this is at equilibrium. Now, this exact equation, or something very close to it, you're going to have to solve in your first homework for the equilibrium angle of attack. I think we say, if you fix the elevator to 5 degrees, what's the equilibrium angle of attack? So what you're going to find is that, well, this equation is nonlinear in alpha. So, well, we're going to get to this lift term in just a second here. But you have this term which depends on alpha multiplying with cosine of alpha. And so the point that I'm making here, if you're given a fixed angle of attack, this equation, it's nonlinear. It's going to require a nonlinear solver like fsolve in MATLAB to get that angle of attack. Have you guys used fsolve before? Maybe on Friday I can do a little example with that too. You've used it? Okay. Perfecto. Then you're going to be all set to solve this equation. So we're not going to do that right now. We're going to simplify this for the sake of the lecture. So let's look at a simpler case. Yeah, I agree. We'll do an example. Okay. If the equilibrium elevator angle is 0, that is, if we said instead of 5 degrees or something, if we just set it equal to 0, then let's zoom out a little bit. I'll grab this. So this last term, the elevator, we set that equal to 0, so that term goes away. So we're going to have this is equal to 0. And then this becomes really much easier because I can divide both sides by cosine. And then, let's scoot this down a little bit. What you find is this lift, which is a function of that angle of attack, is L1 over L2 times the weight. Maybe I'll just put a little box around that. So what we're saying is we got this pinned airfoil in the wind. If we set the elevator angle to 0, then the airfoil will be at equilibrium if the lift is equal to this. L1 over L2 times the weight. Where remember, L1 and L2 are some different distances from the pin joint. Well, okay, that's the lift, but what's the actual angle of attack? So let's take a closer look at this lift. Like, how does it depend on the angle of attack? And I think you learned this in aerodynamics. I'm sure this looks familiar to you. So lift increases with angle of attack. As this angle of attack gets bigger, lift gets bigger until what? This point right here, where approximately we have maximum lift. What's going on here? connect this line over here. Stall. That's right. So this angle of attack, where if you go beyond it, you see this lift is it's dropping off, right? This is our stall angle of attack. And so that happens, I don't know, like 15 to 20 degrees typically for most airfoils. So just have that figure in your mind. But you're going to generate your maximum lift. Yeah, close there. You're going to experience a loss of airspeed because you also have a lot of drag here. Okay. So we point that out. But in this airfoil experiment, there's another angle of attack. And let's say this is the equilibrium angle of attack, where in this lab setting, it's going to remain fixed. So we know from above, if the elevator angle is 0, the lift at this equilibrium angle of attack is L1 over L2 times the weight. So if we could find a configuration where that is the lift, then we know that is the equilibrium angle of attack. If it's a stable equilibrium, I'll just draw this in here because this will become a little bit relevant later. What I mean by a stable equilibrium is if you put this airfoil in that configuration and then you just moved it a little bit, rotated it a little bit from there, is it going to come back to equilibrium? Or is it just going to diverge and flip around? So let's call this like little distance, like a perturbation in the angle of attack. And you know, same distance on this side. That would indicate if it's stable. So just to make this really clear, right there is the equilibrium angle of attack. Okay. So this is a graphical representation of lift, how it changes with angle of attack. There's also this expression for the angle, for the lift, which I'm sure you've seen in aerodynamics. So let's point out a few of these terms here. Rho, we know that is the air density. U infinity is the relative wind velocity. And S, this is the plane form, or do you pronounce it plan form or plane form area? But basically that's if you looked at the airfoil from the bottom, what kind of shadow would it cast? So it's that like area underneath. And then we have here the coefficient of lift. So this is a mathematical expression for how lift changes with alpha. So from the graph above, we know that from experiments before stall, lift varies linearly with the angle of attack. It just goes up like a straight line. So because this stuff, we're assuming it's just a constant before this coefficient of lift. So this coefficient of lift, it depends linearly on alpha, and we're going to say it's equal to this to express that linearity. Oh, that looks a little bit sloppy. I'm going to try to make this cleaner. Okay, so first the coefficient of lift. We're going to take the partial derivative of that with respect to the angle of attack and multiply it by the angle of attack. And we're going to say that this term for now is a constant. So all this is saying is the coefficient of lift is like a constant times alpha. It varies linearly with alpha, and that reflects what we see in the graph. Here's some notation that we'll use in the class, because there's going to be a lot of these partial derivatives that we encounter, and it's a little easier to indicate these partial derivatives as an additional subscript. So coefficient of lift sub alpha is the same as that. I know, we're going to have lots of subscripts flying around, but it'll simplify the notation a little bit. Now, we call this partial derivative a stability derivative. Why a stability derivative? Well, it does affect the stability. Whether this airfoil would diverge from equilibrium or settle back to where it originally was. And how do you get this stability derivative in practice? Well, you could do like a wind tunnel test to get a graph like we saw above so that you could figure out what that slope is. Or you could do a CFD simulation and also get a graph like that. Okay. Lest we forget what we're doing here, I feel like sometimes when we go through the math, it's like, wait, what problem were we even solving here? I don't remember. But let's get back to the point. If we have, we're trying to solve for the equilibrium angle of attack for this airfoil. Now, if we had a reliable value for this stability derivative, we could calculate the equilibrium angle of attack from this formula. So the lift at the equilibrium angle of attack, well, we know that mathematically the lift can be written like this. So I'm just using that expression. And I'm gonna write this out fully right now. But if I have this stability derivative, so this is the lift evaluated at this equilibrium angle. So I have to evaluate this stability derivative at the equilibrium angle, which if this was a constant, then I guess that doesn't really matter. But wait, so all of this is times the equilibrium angle of attack. And we already determined that if the elevator angle was 0, the lift has to be equal to this at equilibrium. So voila. From here, we can solve for our equilibrium angle of attack. We just got to divide by this stuff on the left-hand side. Boom. So if you know this stability derivative here from some experiment or some simulation, this angle right here, alpha naught, this is where we can position our airfoil in the flow, and it'll just stay perfectly still. Okay. So this equilibrium point is important when it comes to linearization. Are you guys still with me? Are you feeling okay? Do you feel totally lost, or is this somewhat clear? I know we're blasting through a lot of math here. All good? Okay, good. All right. So let's get to the transient response here. And what I'm talking about here is the dynamics of this airfoil. How is it going to like move around in the wind if I perturb it a little bit? So if you guys have ever solved a nonlinear differential equation, we're going to have two approaches here. So approach one is you could just directly solve the nonlinear differential equation using some numerical technique. So like ODE 45, that's going to be our choice method of integration in this class for nonlinear systems as well as linear. But what we're going to talk about for now is another option is to just linearize the equation of motion about an equilibrium point. So that's why we solve for the equilibrium point. And we can solve for what are called perturbation dynamics. And you might have an idea of what those are already. So we're going to investigate this option of linearization. You may be asking yourself, what are perturbation dynamics? Well, first, let's define what a perturbation variable is. So I got this below. So we have, does anyone know how to make a 3D animation of ODE 45? Oh, you mean like integrate something and then do a 3D animation of the motion? Oh yeah, you can do that. Okay, so this is the angle of attack. You could write that angle of attack as the equilibrium angle of attack plus, Brad did that in a lecture this past spring. Yeah, I know Brad does some cool animations. Okay, this delta is the perturbation variable. Now, the point here is that it must be a small deviation from the equilibrium value. Okay, so you can take the angle of attack, express it as small deviations from some equilibrium. And then, what are the perturbation dynamics? So the perturbation dynamics for a system are the linear dynamics. And these will only be linear if the perturbation is small. So we'll show that in a second. The linear dynamics, and it'll be in terms of the perturbation variables, and it's valid only in a small neighborhood of the equilibrium point. So that equilibrium angle of attack we solved for up above, these perturbation dynamics that we're going to get are only valid close to that equilibrium angle. So below, we're going to derive those dynamics using Taylor series expansion. And the reason we're doing Taylor series expansion is because it's very general. You can apply this to any nonlinear system. Have you guys used Taylor series specifically for linearizing a nonlinear differential equation before? I'm going to try to be really systematic with it. I know there's different like ad hoc ways of linearizing, but like this way is very formulaic, tried and true. It's procedural. So that's how we're going to do it. You did it in 376. Perfect. Okay. We're just getting up to speed too. You know, it's been a long summer. Everybody needs a refresher. Okay. So I rewrote that nonlinear differential equation. And like I said, the right-hand side, are you going to... Okay, Professor, are you going to upload this file with all your notes included? Yes. I will do that. I will do that. Although I highly advise you to follow along the handout. It's going to help you. Okay. So this right-hand side, it's linear. We say it's a nonlinear function of alpha and our angle of attack. So the way we're going to linearize it, I know I don't have access to a printer, so I can't write all of this along. I know that's the case for a lot of you. Okay. So we can linearize the equation of motion about this equilibrium point by doing a Taylor series expansion of the right-hand side about these equilibrium conditions. So this is how Taylor series works. Okay, so the right-hand side is equal to a function of the angle of attack and the elevator angle. And here is how Taylor series works. It says that that function can be expressed as the function evaluated at the equilibrium values. So that's alpha naught and delta E naught plus the partial derivative of that function with respect to alpha evaluated at these equilibrium values times the perturbation variable in alpha. And then you also differentiate this with respect to our elevator angle. Also evaluate that at the equilibrium values. And you have this. And then additionally, you would have the second order partials and beyond. So this equality holds if you include all of these higher order terms, all right? But we're not going to include those higher order terms. Nobody's got time for that. Let's be real. Let's be real. This is the definition of our perturbation variables once again. The deviation from the equilibrium. So here's why it becomes important that these perturbations are small. So the higher order terms, they're going to involve products of the perturbation variables. Like if you have the second order partial, it's going to be multiplied by like delta alpha squared. Or you might have delta alpha times delta delta. Delta delta? Okay, well, because these variables are small, these higher order products are negligible. Like if you take 0.1 times 0.1, it becomes an even smaller number. So if we ignore the higher order terms, we are left with the approximate relationship. Oh, let me copy this from up there. So we're going to say this right-hand side, ignoring the higher order terms, is just this. The nonlinear function evaluated at the equilibrium plus these partial derivatives times the perturbation variables. So you guys have seen this before in 376, I'm sure. And if we subtract the function evaluated at equilibrium. Let's just write this out. We're going to be left with this. So I'm subtracting this from both sides. Let's just write this out. Okay. So I want to show you something here, relating this to our original nonlinear differential equation. Like this right-hand side, F was the sum of moments, which was equal to, the moment of inertia about P times the angular acceleration. And then this would be that evaluated at the equilibrium conditions. Well, we know at equilibrium this acceleration should be 0 anyways, but forget that for now. So we have the difference between these two. So this is the moment of inertia times this difference. And this is just the moment of inertia times the perturbation acceleration. So now this is a linear equation. If we make this substitution, it's a linear equation just in terms of perturbation variables. So I want to, okay, so I think I included this in the handout already, so you don't need to rewrite it. But we have this. A linear equation in terms of purely perturbation variables. Okay, we have about 5 minutes left. Are you guys hanging with me? We're actually getting we're getting close to the end here. Okay. So we're not totally done yet. We have to do the work of actually calculating these partial derivatives in here because we want to substitute those in here. So let's do those partials so we can finish this up. So I included this for reference. Actually, this isn't a function of alpha dot, but this is our right-hand side, and we need to calculate. Well, first we want the partial with respect to alpha, and then we'll evaluate it at the equilibrium conditions. So let's do that. Okay, so we gotta do like a product rule here because we got a function of alpha multiplying a function of alpha. So I'm going to take the derivative of this first and multiply by the cosine. So I'm going to have minus L2. So this term goes away because it's not a function of alpha. So we're going to have the partial of the coefficient of lift with respect to alpha. And we got to evaluate this at, our equilibrium points. And then that'll just multiply cosine evaluated at the equilibrium. But we got to finish this product rule. So now we're going to have minus L1W minus L2L at alpha naught times sine, because I was taking the derivative of the cosine here. Oops. Sine alpha naught. And then this elevator angle stuff is not a function of alpha, so this is it. At this point, do we have alpha naught, or are we still finding it? Okay, good question. You don't need alpha naught to do these equations symbolically, but in the end, you want a numerical value for this partial derivative because you're going to be plugging it back into this equation of motion, right? So we need to know alpha naught so we can substitute it in, like cosine of whatever number that is, so that we get numbers. Oops, I'm sorry that I'm like jumping around here. So we have alpha naught because we solved for it earlier, and we would just substitute that number in here to get a numerical value for this partial. Okay, let's leave this for now. Let's do this other partial derivative. The derivative of f with respect to the elevator angle. Well, fortunately, that one's a lot easier because the only thing that's a function of the elevator angle is this term. So it's just going to be minus that coefficient. Boom, done. That was the easy derivative there. Okay. Okay, I'm going to plug this in here, and then I think we'll wrap this up for the day. So if we just have, I know we talked about having an equilibrium elevator position set equal to 0, but this math we've done for this linearization portion is generic, where that equilibrium position could be anything. So let's write out that equation in that case. So I'm going to bring this down for reference, and then we'll just write it out, and then we'll be done. Okay, so I'm going to put this like to the side. Is that going to help me if I move it like here? We'll just creep it in there a little bit. Okay. Well, it's this partial times delta alpha. So to save time, I'm just going to copy this. And now I regret having this thing encroach on the box, but that's okay. That's okay. So I take this, and I take that whole thing. Let's stick with this color. I take that whole thing, and now I can remember this, so I'm going to erase it. And I multiply this by delta alpha. And it's good to remember here, when you plug in all of the equilibrium values into this expression, it's just going to be a number. It's going to be a constant times delta alpha. Okay, and then the other term, Eraser Pro. Yeah, thank you. Thank you very much. So our next term is this times that perturbation angle of attack. Boom. So this is a linear equation. For an arbitrary fixed elevator angle. Now, okay, so we're out of time, but what we're going to do next time, we're going to finish this handout, and you're going to see that we end up with some equations that you're used to seeing in dynamic systems. So that's the connection here, that we're going to end up with some linear equations that you're used to dealing with, and that's really powerful because you're going to be able to predict what the motion of these aerodynamic systems is like. Guys, thank you for your attention today. I really, really appreciate it. I'm gonna get this music back. Lecture was pretty intense. I know, I feel like I was kind of blasting through here. I'm trying to get the pace right, you know? Like I said, it's really fast paced, and I don't want to follow behind the other section because I know they're going to be blasting through as well. So yeah, we'll keep the pace up, but I'm going to try to keep it clear. If you guys at any point are like, dude, I have no idea what's going on, please feel comfortable to let me know that. And I'll do my best to clarify things. And I think that's what you guys are doing this lecture. You're just asking questions, and I hope you always feel the freedom to do that. Oh, so office hours. The first office hours is today. Okay, it's today. And so at 4:30, so like in 5 minutes, I'm gonna go to that Discord. If any of you want to come and like test it out, or if you have any questions, I'm gonna hang around there for a little bit, and we can see how that Discord thing works. IQ 195. I don't know about that. I don't know. But that's where I'm gonna go in about 5 minutes. If you wanna, that Discord link is on the syllabus, which is on UB Learns. Other things. First homework is up, people. You can start chipping away at that. Some of it's some math review. This stuff that we went over today, my hat is just going all over the place. The stuff from this pinned airfoil, there's a problem about the pinned airfoil on the homework. So this will help you out. Do you guys have any more class today, or are you all done? Twitch. Sorry, I think I disabled hyperlinks. I don't even remember how to turn it back on. Let's get some Dua Lipa background music for next class. I don't know what that is. What's Dua Lipa? Oh, that's my Discord link. Thank you. It won't pop. Yeah, I need to figure out what setting I disabled. I'm done. Just assignments to do, studying to do. I know it's day one, and I'm already giving you homework. But it's good to get a rhythm going early on, you know? Oh, I like this beat. You in your office. I'm not in my office at UB. I'm at my home. I'm in this little side room. I brought home my desk from UB. I like reassembled it in this room. It's taken up like half the room. I brought my computer from school. So I don't think I'm gonna be on campus that much. Are you guys on campus? How many of you are on campus? I was thinking of maybe having some kind of get together on campus at some point. Lost Templar. Rue, you're in Florida. Nice. Lost Templar, are you in the dorms? Virgin 69 on campus. Is it pretty active? I haven't been there like in like 2 weeks or something. We should do an in-person test review or something. Interesting. Yeah, not a bad idea. The problem is finding a room. Too many students on campus. Yeah, I heard that there's not a bunch of social distancing. Ooh, my 451 group wants to hopefully work with your controls demo project. Should I email you about that? Yeah, email me. Yeah, that'll be a fun one. Okay, everybody. I'm going to close out this stream. I'm going to head to the Discord. And if you want to discuss any further, join me there.